So hello everyone. Welcome to the last section of this workshop, which is also the workshop that I'm gonna give to you guys. My name is Yu-Feng from OpenGeoHub. I am a research assistant / technician. I have been working with Johannes Heiss and Milutin Malakovic together for almost 2 years to develop this kind of ideas or projects, and we almost finish. And I wanted to show you how we go through all the process, and also let you guys explore a little bit at what we have designed and for the community, for the open source community. And so the topic today is accessing big satellite LiDAR from cloud. So everyone know about satellite LiDAR? Everyone know about LiDAR? Okay. A few people know about LiDAR. So I will go to some introduction. So LiDAR is, the whole name is light detection laser range. And it is a technique to actually measuring the distance. And it can be used in multiple different devices, like from the mobile LiDAR or terrestrial LiDAR. They use a traditional way to actually, not a traditional way, but more conventional way to measuring like tree height and stuff on the ground. And there's also UVA LiDARs. They has been using LiDAR sensor on the drone, and they fly through the top of the objects to actually measuring the distance. And in this way, you can see from the top the canopy structure or the ground structure. And to the upper level, which is airborne LiDAR, mostly bigger scale that has been used for regional or national like forest structure mapping or terrain mapping. And at the end is the spaceborne LiDAR. So the LiDAR device attached on space. So they go through the orbit of the Earth and shooting laser beams to the ground, and then record the time they come back, and using this approach to measuring the ground surface height from very far range. And this airspace from LiDAR usually give a global coverage, which very useful for big data projects. And one of the example of the big data from spaceborne LiDAR, it's JEDI. The full name is Global Ecosystem Dynamics Investigations. It has been started in 2018 and from NASA. And using this LiDAR, a lot of research has been done to mapping like forest height and also come to the forest structure. And from the right side, you can see that from the right bottom side, you can see that it's the sample pattern of this LiDAR track go through the ground. And from the last bottom side, you can see that they have this elevation return. So you can find this kind of peak in like 20 meters, which is how the LiDAR sends the first object and then return. And also the ground return is when they reach the ground and they're not going deeper under the ground. That when most of the rest of the photon light has been returned to the has been returned. So you can see these two peaks. So using that, people are able to differentiate what is the canopy height at certain places where LiDAR has detected. And another spaceborne LiDAR is ISAC-2, also from NASA. So these two products are also from NASA. And this product actually, you can see here, I forgot to mention, is attached in the International Space Station. So they're operating by the space stations when they flew or not. And another, this I said is individual satellites. They have their own solar panel to retrieve the energy from the solar. And this data have 6 tracks of the photon tracks. And we used the photon track have been lays like this this kind of low resolution, as it kind of this tracks line along the track. And we have a certain product developed by NASA to actually aggregate all this in individual photon and make meaningful information from there. For example, here you can see that there is classification of the photon using different, version most of all of the photon in the 220 segment track. So you can see that there's this 5 segment, and each segment they have those photon and use the classification formula to distinguish which photon is actually reached the ground, which photon is actually reached the canopy. And in this way, you can actually find where is the ground and where is the canopy. And this line is the median canopy height that we also use to our new publication for mapping the grassland about like outside forests. I wanted to, after finish that, I would just kind of roughly introduce this spaceborne LiDAR. Does anyone still have a confusion about this, or I move into the more detail about the actual data structure from the NASA? Yeah. Okay. Sounds good. So this is the example from the JEDI. This is the JEDI product. This is the picture on the right. You can see that is actually the actual orbit from JEDI. For sure, it's not the the right projection. If you see that the beam come from the right and go to the left and disappear, but actually this is if you put in like bolt, and you can actually see that they're circling around the Earth. But most of all of the spaceborne LiDAR, they have organized the data in the way of following the orbit. So this image show better result as one of the data you can download from the JEDI or ISAT official API. You can see that there's all these individual HI files, that each HI file represent a part of the orbit that they saving this into HI files format and then expose it on their API. And this is actually not really trivial, because in order to find all of the points in such a certain area, you have to go through all the orbit and try to retrieve the possible file from the specific area, because the orbit from here, the last one from here, the next one will go under, and it will be maybe 3 months after you will be in the new orbit coming to the same area, like same area to across the last orbit. And it's a little bit not trivial if you do like a spatial temporal research, because you're always interested in a certain area of interest. And this format will take you a lot of time to actually find all the information you need. So in our projects, to actually make the data more interpretable, but more easy to access, we start thinking about how can we reorganize this data format into a more optimized way. And so that we're looking for a lot of solution online, and we found this kind of initiative called Parquet. As also, so everyone know about Parquet? What is Parquet? Anyone have any idea what is Parquet? Yeah. No, it's actually the floor. The floor. So I'm sorry. So Parquet is actually when you do the floor, they have for example, you can see under you. There is a part of the wood pieces, and they are actually called parquet. And in the contrast of the left one's tile, that you may be more familiar when you do geospatial data. Everyone do things in tile. And what is the difference between tile and parquet? Is tile, you have a very regular shape and very connected into upside, left side, right side, downside. But the parquet you see their parquet has been maybe longer or shorter. It depends on what is your room size, what is your room structure. And the parquet can patches in the more irregular way. And this data format, instead of like in the contrast of tile that used mainly for raster data, is better for irregular point data for factor format. So that is why this is what looking like getting to our eyes. And yeah, this is the example that the Jedi point in all of the Europe. You can see that this is not a square data format. It's a lot of points, and the point can be scattered around into not irregular line. So Parquet is deemed for working with mostly factor data in this characteristic. And so back to the Greg said that Parquet, which is this open source project, it's the actually like unlike open source projects, not only just the material that you put on the floor. It's it's from the Apache, and it's the oriented data format that designed for efficient data storage and retrieval. And they have three important features here that have been doing so well for their data storage. One is they have very high compression. The second is they have the partitioning features. And the last one, they have a cloud native format to allow user to do lazy loading. So this is one of the research conducted by some Planet group to, I don't know if it's a Planet group, but it's a guy who worked with the Planescope, I assume, and he tests a little bit of the Parquet with other different factor data formats, and they found out like they have very faster data access. If you access for the pandas using Python, you can maybe have 5 times faster, and then when you do data storage, also have lower size. So it's really efficient to store and transport the data. And come to the first feature as data partitions. So the partition is work like this. You have a big data side. We have the big data. And according to the calling information, you can split into small data chunk, which is a small data file, not just like, individual chunk, but it's actual file. And in this way, you can do, for example, split by the temporal range. So this case is for a month, and you can also split as the altitude line. Okay, so it's kind of like a spatial feature. So okay, above 30 altitude and on the below 30 altitude, I can have 3 different chunks. And you can do hierarchy splitting. So you can first split by the spatial, and the second split by the temporal. And that made me feel maybe this is interesting to actually process the data, because we can actually rearrange the orbit and using this splitting to actually relocate all this file into different individual chunk of time and space. So this is the example that A file, B file, 3 file, if it have the same month, they can be put in one single chunk. And if you like another month, they can put to another partition together. And this made us think, because when we try to index a file, we cannot just read all the file together and start indexing, because the file could be too big for our local memory. And using this, you don't have to communicate the information from different files. You can just do parallel processing without thinking about your neighbor files. So using this way, we try to design a pipeline to create the partitions for those spaceborne LiDAR. So this is an example that when you do like Jedi coverage, from the time they do the orbit, you can see that the orbit start playing around, and then some of the orbit, they will fall into different spatial temporal block that we designed for them. And all of the point which in the file have these spatial temporal features, they will be put into the same. So for example, the Jedi 01, it can be put part of that in the partition 1 and the other part in partition 2, and the 02, it can be part of partition 2 and 1 and 2 again, and 3 can be 2 and 3. So in this way, we can just reorganize all this file. And using that, we design all this spatial temporal blocking. That's how we name it. That you first have a predefined of the tiles, the tile that you are interested in, and then you just keep running the process throughout all the eyesight and Jedi original format. And we really need this work? That's also we need to have the reason why we need to do that. And there's two examples that I'm involved in this publication. The first one is my own publication where I used it to do global to local mapping, because I can query all this spatial temporal cloud as fast to actually do local prediction, local enhance in my digital elevation model. And another example is that we use this to design a sample for short vegetation height mapping. So this is one of the paper that published from our partner in under Global Pasture Watch. So we do spatial temporal blocking, and then we took the small block and we designed a sample point to predict the median vegetation height that mainly focus on the outside forest ecosystem. And this is the publication are all published so far. So if you are interested, you can take a look. And by the way, if you have a laptop, I hope Beatrice gives you the access to the slides, because after all, we have gonna do some, hands-on. If you are interested in doing some hands-on, you can access the slides and also the notebook that the hands-on material in there. Yes. So I talk about use cases, and we also try to encourage people to access in the more easier way. So we do some data access and visualization in the stack. So we put it on the stack that designed by ourselves, an OpenLandMap. This is the surface that store mainly global data, raster and factor, and the data on here are all CC by license, as you see over here, so you can freely use it and without any restrictions. And this is the data that we put on there for the JEDI example. And we also have this exact example. They are both ready on the online, and it's ready to be exposed. And then I already using that for multiple use cases. The next feature I want to talk about the Parquet. It's the lazy loading. So I hope that people are more also know about lazy loading. Maybe someone didn't know about this? Okay, yeah. So lazy loading is like that. So you have a client and you have a cloud service, and instead of like reaching all of the data from the cloud, so the data chunk is actual data places that is on the cloud. Instead of first interact with all the data chunk, you go to the metadata to actually understand how this data being structured. And the lazy loading are the way of using this metadata. You can define some predicate, some filter. And this filter will select only the data chunk that related to give you back to the client. And also using the metadata, you can be more efficient because the data set already know that what kind of data you are wanting to retrieve, so they can schedule in parallel to let you retrieve all the data into a more efficient way. So in this way, you don't have to read the data, every data locally, and then filter out those useless data. Okay, Chris?
It's like the lazy loading, I mean, as a general concept, right, is you don't know upfront if you will need everything, but you need the reference already. So that's where you write on the metadata and linking to that. And then during the analysis, it becomes clear what you really need. And that's why in the beginning, you don't load it yet, just up the moment that you really need it.
Yeah, it's a good rephrase. And I think people are doing perception, because for this lazy loading, we do, for example, the spatial temporal for example, the web surface. Web surface is also the part of the more lazy loading, because user have selecting by their own predefined criteria to actually retrieve the data. And then in that way, they already know that what kind of data they wanted to get. And the data not related to that, they just don't retrieve it at all. So there's some different way, but the main key is you need to have like a cloud native format to store this metadata in order to be able to filter that before everything's come to the client side, if that makes sense. So back to the Parquet data, they actually have two mainly feature, which is called column selection and Parquet push down. So the column selection is like the data in the Parquet data in the data format. They have been split according to they have been stored in the color or oriental format. So you can only read part of the columns from the data. For example, you have 1,000 columns and you're only interested with 3 columns. So you don't need to read another 997 columns. And using Parquet, you can just specify what kind of column you wanted to read. And then you like maybe just 0.3% of the data retrieval you actually do because you don't read other columns. And another is the Parquet push down. So you can actually specify the information for in the row. So for example, I want to have the time between 2005 and 2005 and 2006, and I define this, and the metadata were interacted with the Parquet to actually exclude the data before 2025 and exclude the data after 2026. In this case, you only read 1 year of data, so you read last row, and you also save the time and be more efficient of reading all this data. So that is the last features about this lazy loading. And there is a lot of software that working with that. This is more in for the Python environment, but also I believe in R. Johannes worked with all of the R API, but he is not able to be here because he have newborn children. So I'm suggesting not to contribute so much, but also in R you can find those API for partial arrow and polars and DuckDB. And this is what we were gonna to work on that a little bit on the workshop. So I will demonstrate it. And if you have interest to play with all this notebook, you can follow my step. Arrow and Parquet. Yeah, the Arrow is one of the open source software system, but mainly for the data formatting. But they retrieve the different data sources just like Pandas. You know, Pandas is also one of the software that you to access the data. But Parquet is the data format. So software and then format, they are different concept. So you can read Parquet into different software, but you can also use software to retrieve different type of data. DuckDB is one of the API also to retrieve. It's also the software to retrieve different type of geospatial data, especially factor. Yes, and I will demonstrate in how DuckDB work and how other software work in their own specialties. GDAL supported? GDAL supported, yes, but it's still, I would say that in the integration process that you still cannot integrate so well in the QGIS in the older version. But now they have a lot of new version. But the good news is like 2 years ago, I was working with this project, and probably I searched on the figure. There's probably 2 or 3 figures only. And today I was searching on Parquet figures, and there are like tons of visualization already there. So I believe that the community is already picking up for the Parquet format for a lot of data storage. So no, this is under investigation. But yeah, we will stay tuned in the community to see that how this evolve. Yes. Okay, any other questions? Okay. So I will demonstrate it, and if you're interested, you can take your own laptop. If you are wanting to just see me improvising, you can just look at me doing this. So first of all, we will get this notebook. This notebook is written by me, but I didn't want other people to play with my notebook, so I lock it. And the only thing you have to do is to make a copy in your own Google Drive, if you have a Google Drive. If you don't have a Google Drive, you have to probably make one Google Drive. So now I can start using this. Yes. And this is what we are going to show. So in this script, this workshop, we are gonna access the Jedi and ISAT view this cloud native parquet, and we will go through different software to see that how they interact with the data. And first, to really visualize the data, you can go to stack, open them, map. This is different keyboard. Oh, okay, they gave me already here. So you can go here to visualize a little bit of the ISAT and Jedi. And this is Jedi, then we can also get ISAT.
How big is it of these chunks?
Yeah, we will show you later. I cannot find it. Anyway, I will show you later from here. First, the Jedi. So you can see here, you have all these items which relocate to the spatial temporal block.
So how big is each block?
Okay, how big is this block? Usually the data file is around 200 megabyte to 2 gigabytes.
Okay.
And the smaller can be still smaller than that, but most of it in this range, because according to the literature, they have been the best size for a single parquet to be read and write.
And how many points approximately one block has?
About 2 to 3 million.
Okay.
Yeah. So you can go to, for example, a different block, and they will kind of visualize how this point actually looks like. But this is what I transfer into the Club GeoT. We wanted to show that here. It's not the optimal way, but if you go to this single block, you can see that how this data has been visualized in the spatial temporal range. And also you can just download over here, no copy URL, and then, and you can start downloading those data into your local. Yes. And you can go to another, whatever you like, and they will just locate it where the data are. But this is all not my favorite way to work with that. My favorite way is this one. So I also create a stack item from using the GeoJSON. So they give you like the entire information from all of the partition tile that we have. So you give you the information of where is the item and what is the size of this. So for instance, this is 110 megabyte for this tile, and they will have 900K points in this file. And then what is the starting date of this? What is the end date of this? And they give you like a basic information. So we're gonna like play with that. So we can just copy this one, and we open on here. It's the same path because I already read it. And you can just use the GeoJSON, not the GeoJSON, sorry, GeoPandas to read the file into your local range. And this is the showcase of the tile. And then we're gonna to write this to visualize it. So this is the visualization of all the tile distributed. And that what we're gonna work is with them. So the first thing that I'm doing here is to have an overview of how big is this data set. So this one tell you the total megabytes of all of the items and divide by 1,000. So it's the gigabyte size. So this data set has around 700 gigabyte in total that you can play with. So it imagines that you wanted to download this 700 gigabyte, how much time you will take. But if you were stored at the cloud, you only select what you need. You don't need to download this 700 into your local site. That's the big benefit. I can just play with the Google Colab. And then we're gonna do some demonstration using the.
Can you make the font bigger, please?
Oh yes. Okay. Where's the plus?
Thanks.
Yes. Great. So to actually play with this, we designed some small places that we can play with. So this one is, I download this GADM, like the boundary of the country. And I select this one, NLD, which is the Netherlands. And using this data, I can try to query the data only in the Netherlands. So you can see that this is the JIDA tile. I visualize it. And they overlay with the this country GDAM data set. And if you, for example, I'm the big user of the Netherlands, I don't need a global tile. I don't need to access this tile from all of the places. I only need the tile like overlay with the Netherlands boundary. So this is the actual look of the boundary of the Netherlands with all this tile that overlay with that. And you can see that there's a line of the Netherlands just because JEDI have like a range from 52.5 altitude down to 52.5 altitude to the south. So they only have part of the places has been covered with JEDI, and it's around, you know, added Utsle down to Utsle have no JEDI apparently. So this is the visualize, and then we can start reading all this tile, or read all this like information from the JEDI and see that. So first thing, we get the bounding box of the province of the whole Netherlands. So we know what is the range of the Netherlands. And then we use that to intersect with the JEDI data set. So in this case, you are supposed to get only the JEDI that belong to the Netherlands. So you only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rows. So the total was, as you see, like 3,000 something, and now you only need to read 10 rows of the data. So this is one of the data that we search to retrieve, and then we're gonna do some demo just to try to access one Parquet file, so we can practice a little bit of using this cloud native format, and before we enter it into the production. So the first we get one of the data. And to get easier, we just download it to our Google Colab. And you can see that the data are being downloaded. And it's about 192 megabyte of the data that you download over here. And then I can start reading. The first one I want to try is to use GeoPandas to read, because Parquet also can be read by GeoPandas. So if you work with GeoPandas, yes, you can read the Parquet also. And then I can just read everything. Yes. So you can see a little bit of the data shape also, what this looks like. So you have.
Can you explain us now when you read it? So it has projected coordinates, right? But how do you know, for example, coordinate system? Does it automatically fetches it?
What do you mean?
Like so projection system, bounding box, things like that. Does it treat it as a geospatial object or just a purely a table?
Parquet is purely table.
Okay.
GeoParquet is with the projection and the spatial
but
feature.
Now this one that you read.
We have the geospatial feature in this, but using the GeoPandas, you are not able to work with them.
Okay.
Because they don't support geospatial and in the pandas.
Okay.
Yeah, sorry, it's a bit weird, but this is what we got.
Does the GeoPandas do lazy loading? No.
GeoPandas read everything.
Yeah. Okay.
Yeah, there's no lazy loading. So you can see that I read 95 columns and 1.3 millions of row. So I read everything, and you can see how fast it read. It's 4 seconds for 190 megabytes of data. It's still very amazing. Okay. And the second one, we can access a few PyArray, and PyArray, they do support lazy loading stuff. So that we wanted to try here. I think I already tried it. So we read the same data, but this time we apply a filter to the data set, which is the quality flag. So you have to pass the quality flag in order to be used this concept. And then I read into this filter data, and then to Pandas is actually to retrieve the data that I predicate to actual local memory. And this is actually reading spot for all the data. And then we can time up the seconds, and you can see that the data is 1.3 millions. But using this, you only read 1.08 million, but also 95 columns. And it takes 3 seconds, and this one take only 1.6 seconds because it already did some filtering in advance. But also, PyArray can be also faster than GeoPandas in this sense. Yes. And after that, we can also try to not only filter, but also select the column that we say we can do the column selection. So this one, I select only 3 columns. The RH95 is a relative half 95 from the Jedi. And latitude and longitude, so only 3 columns. So if you read this, only 0.05 seconds. I can read 1.3 million of columns because we only need retrieve 3 columns instead of 95. So the reading time is extremely faster if you only need less information. And then you can also combine 2 of the features together. So I can use a column selection, but I also use the predicate push down to read the data in the quality flag, and also select only 2 columns. And you don't actually need to read the quality flag into your local because you're already filtering out, which is also like very handy. So you can just do every preloading in advance and then read the data that you actually need to do the further analyze. So in this one, only 0.06 second, which is very, very fast. So yeah, this is the way that we can read the.
Just again, could you also read from the S3?
This is I'm gonna show also the demo.
Okay.
You just kind of like spoil my old work right now. I know you are working with S3, but yeah, let me maybe got there, so you will see. And the next one I will read is to using Polars. So Polars is the another open source project developed by an Amsterdam team. And you can see that they have been documenting everything the open source surface from this, and this writing in the backend of Rust, and they have Python and R API, I believe. This is compared to Pandas, so you can see that Pandas is maybe more cute, and Polar Bear is more aggressive. So it have been more powerful than Pandas. So I think that is the design idea back from the team. But I will also assume that the ground bear or the grizzly bear also very aggressive, because it's what I met them in my holiday. Okay, so now we can use these polars to actually have the same logic to read the Parquet. And the function to actually read the metadata is called scan Parquet. So you can scan the file that we store in local and select, and using the filter, just the syntax difference, but the ideology of working with Parquet, it's more or less the same. So the idea is that you learn how this idea work, and you can adapt to different software, and you can develop your own software also. But I would suggest that you choose something that you really you're familiar with, and then you just work on that. So they can also using the same thing and collect and to pandas to see that how this work. And this is also similar time, so 1 second to read, and to read 3 columns and filter out from the flags. So this is how you access through the polars. And for sure, you can try different options. And later on, we wanted to show and another things from the last one is called DuckDB. So DuckDB, does everyone know DuckDB? Okay, that's very cool, because DuckDB is actually a very cool stuff. It's more like a SQL-based database management tool, and it's write mainly on SQL, but they have a lot of extension API from Python and R also. And the best feature I would say from the DuckDB is you can actually play with the spatial GeoPandas, like the GeoParquet, because the data, the software that we mentioned, Polars, and PyArrow. They mainly work with Parquet data. So Parquet is the start of this initiated column or ordinated cloud native format. But the GeoParquet is slowly adapting these few years, and DuckDB is one of the software that can actually work close with the GeoParquet format. That's more handy to interesting in processing your data in the geospatial concept. DuckDB is a good tool that you can explore. And to first work with the Parquet, we have to know that Parquet is a more efficient way to access the data. So they don't store the data in the stupid way. So they don't use they don't use the well-known text. They use the well-known binary text, which is the binary format of the geometrics, which is still which is way faster and more efficient to store geometric information. So when you work with GeoParquet, you have to convert from the well-known text to a well-known binary in order to work with the geospatial filter. But this is more like if you read this code, you can apply this function, and you will run all this immediately on the backend, so you don't have to worry about that. So in this way, I need to get my well-known text out from my polygon that I have, so I can use that polygon to interact with the GeoParquet in DuckDB. And this is just start with the first easy example to query local file read into a DuckDB. So it's very similar than the former work that just read the file using this SQL to read the file and then open everything. So you have 95 columns with 1.3 millions of rows. And then in this case, I can get spatial package inside DuckDB to use. And they empower one of the function is to do intersections. And this is more like if you know PostgreSQL, they have a similar function to actually do spatial query. And you can do that based on giving your well-known text and from the geometric and interact with the geometry inside the Parquet. And in this way, you can do spatial filtering already.
Just a second, when you import it to DuckDB,
yes,
is it in the memory or it creates a file at DuckDB?
In the memory. In the memory.
In memory. That's
yes.
Interesting. So you have just a database in the memory.
Database in the memory. I don't have the database. I only have the table in the memory at the end.
Okay.
Yeah, because you
import to DuckDB. I mean, in some standard databases, when you import it, it creates local files.
DuckDB is the database management software. So it's a software. So you don't have any overhead. So basically, the more storage, the DuckDB is just code, just the code, and Parquet is the file.
And is there a quick GUI for DuckDB?
I believe there's someone develop it, but I'm not a fan of GUI. Yeah.
Could you get an interactive map now very quickly?
I believe there's some QGIS plugin there using DuckDB
like
for Parquet.
Kepler GL. Could you get a quick interactive map?
We can try.
Okay.
We can try. Yeah. But this is just fundamental process of using DuckDB with this format. And okay, so here I see using intersect to retrieve the data, and it doesn't take fast. I believe the intersect is also taking time to actually work with the geospatial data. So it doesn't really take fast. But if you have to do the intersects anyway, why you don't do it before you're reading them? Because when you read the data directly from the clients, from the server side, if you're only interested with the boundary of the Netherlands, you still need to do an intersect. An intersection in the GeoPandas, you have to also count the time on that. And using this way, you already retrieve that before you're reading everything, which is more efficiency of your memories management, but also maybe still faster than reading everything and do the intersect locally. So you can also apply the same as column selection and the spatial like filtering here. So this is crazy. So you can plug everything and get all the data. So this is how like DuckDB work with Parquet. And last things I want to show is the demo of reading URLs. So as Tom mentioned that, can we read from S3? Yes. And more interestingly, you can directly read from a lot of S3 stream at the same time from the single section of the code. So I was reading here the URL from the Centile that we are using. So it's a lot of URLs. I would say that it's 10. So you can see that all of the files in different year and different geospatial blocking that I read everything that I need. I print out everything that I want to read. And I can read Parquet from just the URLs, the everything all together and into some single code. So I can do the intersection with all the URL that I'm reading in, and also selecting the columns that I only need, and then and also the quality flag, and using the URLs list from the Python you give them to DuckDB. DuckDB will interact with all these items, all the list, and use the parallel processing to get everything.
Can you read in parallel?
Yeah, it's default reading parallel.
Okay. So if you have many threads, it can go.
If you have many threads, you go faster.
Okay.
And this is the laptop from like Google Colab, so you don't expect to have some parallel, but you can already see that I read a lot of data here in 33 seconds. So how many data I have read? Okay. So about 2 million points because I do a lot of filter, but you already done a lot of filter and then everything, what you need to a local. So this is how it shows. Yep. And later on, the last demo, because when you use wild binary text, it's still not easy for most of the user. But you can do one of the steps I'm doing here is to transform them into the format that GeoPandas can interrupt it, and then you can interrupt it and convert into GeoPandas geospatial format. So GeoPandas the geometric columns that you can save as GeoPackage or GeoJSON. So you can do some simple visualization, or you can just retrieve all the data and not saving in Parquet, but saving in shapefile or GeoPackage and deliver to the colleagues who is not really interested in my work. So you can do this by setting up as well binary geometric to convert the geometric from GeoPandas to binary that you can be read from GeoPandas. So we have wild binary, can apply this wild binary loader and convert into geometrics, and then we can save that into GeoJSON. So this is also one of the features that when you work in the backend, you don't really care about visualizing in QGIS, but in this way you can sample a few points and visualizing in the QGIS, and you can see that it takes longer time because when I convert to geometric format, it's actually like inflate a lot of space as not efficient storage, so they take time to actually read. But you can download it to visualizing the QGIS, but I think this laptop don't have QGIS, so you can do it at home if you have QGIS or like ArcGIS installed it. Yeah. I think I'm almost done. Maybe I have to quit for the section, right? I do like 1 hour section for. Yeah. So I think I don't have to really do so much for this 30 minutes, but yeah, this is the things I wanted to show. We do have some summary over here based on that we try and expose a little bit of this cloud native format. And this is some take-home message where we will give. So the first one is the GeoParquet specification. So I have this column orientation to support our column selection. And we also have the structure to use the predicate that which is in document. They say it's a row group. So basically, they arrange like similar data in the same group. For example, they are the same age, they are the same years, that they will put closer with each other. Using this row group, I can search the minimum and maximum of each row group and actually do the quick filter that the information that's far from them, but it's all done by their Parquet internal format, so we don't have to worry about. But this features that support quite a bit of per-decay pushdown, which is filtering before getting the data to your client side. And then we compare about DuckDB, PyArray, Polars, and GeoPandas for accessing Parquet data. And this is a summary, so you can read and write GeoParquet at any format. So DuckDB, PyArray, Polars, GeoPandas, you can both read them. But GeoPandas have no ability to do column selection or per-decay pushdown because they don't work with cloud native format. So when you want to work in cloud native format, you probably have to choose Polars or PyArray or even DuckDB. And for the last things is called a special filter, so you can intersect with the data set. That's only for now has been done for DuckDB. So if you work with the PyArray or like Polars, even like it's fast, but you have to do the intersection and also convert geometries by yourself. So this is the kind of like a summary of the software that we're testing.
So maybe in this table you should put the times, you know, the speed of access or processing, because now it looks obvious that the DuckDB is the best solution, right?
Yeah.
For this table, but it's just much slower, no?
No, I would not say it's much slower. Okay, so for example, if you read here, 3 seconds. Okay, 3 seconds to read from DuckDB for the whole data set.
Yeah, the other one was like 0.5 seconds. So
No, the whole data set. I mean,
okay.
This one is not the whole data set. This one is the whole data set reading pandas, which is also 3.8. It's slightly slower than DuckDB, I would say. And this one I didn't read from there, so it's not. Now we can test it a little bit of reading everything, right? So let me test.
Then it could be that the DuckDB is just most universal solution, no?
Yep.
For this.
Yep, it could be. So.
But is the idea of DuckDB that natively works with the Parquet, or does DuckDB have some other more optimal format for data? Does DuckDB works natively with Parquet? I mean, is it? That's the idea.
DuckDB work natively with Parquet. That's a good question. You have to really go into the.
Could you expose on Stack some format which is more DuckDB, you know, compatible?
I think Parquet is already DuckDB compatible.
Okay.
It's the same as DuckDB read Geo package, DuckDB read JSON. They have the similar workflow that they use. So I expect, okay. So that shows that, yeah, your Tom could be right, because when I read the whole data set, using this PyArray is still faster than the DuckDB. So maybe this is spatial features that they are trying to figure will slow down the process. That's could be right. You know, 2 seconds, or like 1 second faster than DuckDB and also GeoPandas. So this is also need to be considered. I think it's a very good point. It's we need to also do a little bit benchmarking on this speed, but functional wise, that's what the summary has told you about. Yeah. Okay.
But can you then do a spatial comparison using those spatial features of DuckDB, but implementing it or doing the same strategy with the other ones to also get a time comparison?
Spatial features. There will be more complex way, and I will say that we have tried first is, for example, you get a polygon, and then you first get the x minimum, x maximum, y minimum, y minimum, y maximum, and then you have a column in the Parquet data that give you the latitude and longitude for each point. And then I first filtering by the boundary of the form, so like a bounding box, and retrieve all this data to the front. And then using that, I need to still intersect with the polygon when they read in. And but since the PyArray and the Polars doesn't work with GeoPandas, you have to create your own geometric. So for example, you have to convert the XY from the latitude, longitude to a geometric. You have to create by yourself the geometric point and then intersect again. So you can see that this feature on the back is a bit more complex.
So
And-
it's that what DuckDB does for you, right? So no.
No, DuckDB already work with the geometrics that if you are so if you do pyro and the polars, they don't interact with the geometric, so you will get an error when you have a
What
geometric
if
in your
you,
column.
like you want to load, you have all this point data, the whole world. Now you just want to load whole world data, but only forests. So
you have a forest
you
mod.
need to overlay with the land cover map, let's say, and just say, I just want this class. How would you do it?
How would I do it? That's a very good question. Because you have a pixel, right?
Yes, you need to.
You need to convert to
You need to
polygon.
extract and see where
You need to convert to polygon in order to do that. Otherwise, you have to overlay
I mean,
all
you
the
could do
points.
it in parallel. You could also do the tiles of the rasters, right? And then
Yeah.
every time you load a point, you overlay and you drop everything else, and you just keep the points that you need.
Yeah, but you load everything, so you already waste time. So
There's no way to get in DuckDB that raster.
raster, it's just like a spatial space-time overlay. You need to overlay all the point in order to know what is the actual value of the raster for that point. So you need to run the overlay in order to get that information.
But could you do that in DuckDB? That's the question.
Or space overlay? No, I can do it in Scikit-map, but not here. Scikit-map, it's the package developed by my colleagues. But they're also optimized for
So there's no
space-time
way in
overlay.
DuckDB to have a raster, so you can do also some spatial filter or query.
Yeah, but if you know the behind of the space overlay, you know that how they actually work. They have to relocate every point to actually get that things out. So you have to actually get every point.
No, I know, but if you do it per tile, if you have, I don't know, how many tiles you have now?
Depends on what the tile size. We went 3,000 tiles.
3,000. So like you take one tile
Yeah.
and you load it raster in DuckDB.
Yes.
Then you do that spatial subset, and then you just export what you need, right?
Yeah.
That could work.
Yeah, that worked. That actually have been done in my first paper also. Like we load this Jedi and ISAT into the end, and it will overlay with the digital terrain model and filter off the point that is offset with the digital terrain model.
You could do that, right? So
yeah, but in this case, you still need to read all the points into your front end.
Yes, but if you run it in parallel, you could do it. And
yeah, exactly.
And then you keep only the points that you need, right?
Yeah, exactly. So that's correct. So it can be done in multiple ways, but this is just the demo of reading by the people who don't have like a HPC server. So as we OpenGeoHub do, we can read everything in parallel, and you just have more thread to everything. But if you don't have the storage and don't have the capacity for computing, using the code lab can already read 1 million of points in the matter of seconds using the Parquet format. Yeah, I don't think that I have so much to prepare because I was expected someone wanted to work on that. There's some problem with that. We can store it in another way. But yeah, if you can earn early, we can also, check a little bit of, we can also end early, right?
Yeah, yes, please.
Yeah. So the last thing I would do is...
This is much bigger data, no?
Yeah.
Yu-Feng, can I ask something? Maybe with the GDAL integration of DuckDB, can Tom's question be answered? Do you think? Because there's also a special extension in DuckDB where they allow the smooth integration with the GDAL. So maybe we can do some sort of overlay analysis with GDAL's commands, not directly from DuckDB, but
okay. Interesting. This field is developing so fast that I cannot.
Yeah, it's quite recent, I think.
Yeah, but it's interesting to know. Maybe we can do some tests later. Yeah. Yeah, finally, I just show a little bit. So the way we are playing with ISAT with all this function, and you can do some take home with you of the data. You can play with this. Okay, can I ask this? Okay, this is the ISAT data that we use for our paper also. So you can see that this is all the ISAT data. You even had Antarctica in this data set, but we don't play with Antarctica. But you can have like a data of this, and you have the similar structure of okay, this is some small island, so I only have 2 points of this collection. And you can play with a lot of different. Okay, this is some island from Norway, I guess. So you can have all these points, visualize it here. It's the same as we do in GDAL, but they have bigger size. So it's 9,000 partition over here because we have more dense collection and points for ISAT. And this the last thing that will show. It's just how big the data is. So Jedi is about 700 that we deal with, and this ISAT data set have 3.6 petabyte. So good luck with downloading the data if you really just want it to work locally. But using this, you can play with 3.6 terabyte of data in a matter of seconds using the Google Colab, this kind of poor infrastructure. So that's all I wanted to present for now. And I will open for a question if anyone has some.
Yeah, so we would like to extend this to add use the Kepler GL. I think it's very compatible to visualize the data, right? That could be the easiest way.
Kepler GL, I mean?
Kepler GL, yeah. I mean, you said you could export the GeoJSON and drop in QGIS.
Yes.
But you could also just set up a very quickly an app, and then people can explore and click on points. And
yeah, actually, there is some app developing already from other team using DocDB in the QGIS. So you can try to search the DocDB plugin in QGIS, and then they also work directly with the S3 Parquet file. So yes, I think there's a lot of development coming up in this field. And yeah, what do you think is good to add on with
this density map? How did you make that, for example?
The density map, just what I showed, how many points it being one tile. So we just plot the density map of the tile the number of points in just each tile, and then we visualizing this. And it's just like,
You just export the geo package, or
yeah.
Okay.
I just export a geo package to show that how this data looks like in the global scale in this way, in this kind of like a tile-based way to show.
This ISA2, it continues, right? It just keeps on. They keep on making this data. It's
yeah, I don't know if I good to say. Maybe they have to cut off this, but ISA2, they were trying to extend it. Now it's version 7, so we as OpenGeoHub we keep downloading and we processing into this data format. In a matter of a week, we can do that. But ISAT also have suffering from the Donald Trump have the budget cut. So I don't know if they will continue, but it's all an impact on the NASA product that they probably will stop because of the issue with the White House.
Okay, so and let's say they just continue, but they are always new. They have new parts, no? There's always the part is a bit different. So eventually they can cover every, let's say 30 by 30 meter. You'll have a 1 point at least.
Yeah, but this doesn't make sense. Like if you have a forest cut that you cover in the same different temporal coverage. So even like they cover every ground truth, you have very big, huge range of temporal differences. You cannot even use it for forest mapping, for example, because it's
but
just
let's say
compatible.
Theoretically, we just want to know theoretically when could they have, for example, how many years will take to have every 30 meter?
So 4 years they collect the data. It's about 2% of the 30-meter tile.
Okay.
If you want to do 30-meter mapping, you probably need 50 years more.
50.
Yeah, it's not able to cover every pixel.
Okay.
But if you downscale to 500 meter, they cover already 50% of the pixel.
So 500 meter, already 50% of the world, there's at least 1 point.
For 30 meters, there's only 2-3%.
Yeah. Okay, but it's this ISAT, it's a really revolution, it's There's so many applications, right? I mean, almost maybe European Space Agency should consider something like this. Because we have now about 4 publications that are based on ISAT, right?
1, 2, 3, maybe three.
Yeah.
Three.
3 publications based and more publications coming. So it's really so valuable. And how many points ISAT 2 in total? You estimate
To
growth
25
potential?
billion that we can
25
use.
25 billion
But
points.
for sure, you need to apply
Fil-
a lot of filtering if
filtering.
you are doing different tasks.
25 billion points, yeah. So let's see more questions from the audience.
Okay.
Anybody using ISAT 2? Are you using for your research? Can we see your hand? Are you using ISAT 2 for your...
Everyone using Jedi? No.
Jedi will not be continued, right? Jedi is...
Jedi is continue again. So they back to track. So they're
they
they
have
start
a new
collecting
Jedi.
again.
Okay.
Yeah, they rejoin. So up and
But
up and up.
still they come only to half of Netherlands. And
Yeah,
then
but you do tropical, it's more than enough.
yeah.
Yeah.
Okay.
Okay.
So yeah, we'll stop then. Then we'll stop. Thank you, Yu-Feng. That was very useful. And don't forget, there's a collab. You can play with it, and also you can access the videos from next week. You can see in more detail how it works. But
Okay.
Yu-Feng's been working now 3 or 4 years with this. I think 3 years, and now continuing on above ground biomass mapping. We want to switch from just purely ISAT to above ground biomass and more like what we call the what was it I also
What do you
forgot.
want to say?
Not the IRD, the PRD.
Oh, policy relevant.
Policy relevant data.
Yeah, there's still a long way to
So
go.
we're going to that. So okay, thank you, Yu-Feng.
All right, thank you, everyone.
Continue recording, doesn't matter. We have